Just a few words about Pete. He is a molecular ecologist and agroecologist at the James Hutton Institute in Dundee, UK. His current research is focused upon the commercial application of biology and ecology, underpinning legume crop performance and coexistence as an intercrop in the face of land use and environmental change. He obviously also works on tomato. Pete is the leader of the work package 4 of TOMRES.
Hello, I'm PeteIannetta, and today I'm going to be talking briefly about only one of the tasks from an EU-funded project called TOMRES. This task concerns the use of the systematic approach to study multiple stress tolerance in crops. The TOMRES project is focused on identifying integrated approaches to address water, nitrogen, and/or phosphorus deficit stress tolerance. These three resources are arguably the most important things required for crop growth and productivity. Nevertheless, these inputs need to be used sparingly. Also, there are climate challenges, and there's a real need for multiple stress-tolerant crop plants. Tomato was chosen as it is an accepted genetic model species, like rice for grasses and mid-cago for the legume family. As a member of the plant family Solanaceae, tomatoes are also closely related to other socioeconomically important crops, such as potato and peppers. As a model species, the hope is that whatever is found for tomatoes may be transferable to the other crops. Tomato is also very important commercially, with a global value of around $190 billion annually, and can command import values of up to £2,000 per tonne, which was recorded in Germany in 2018. This slide shows the TOMRES work package structure, highlighting the tasks carried out by Hutton in the dark grey text boxes. We lead work package 4 and are responsible for data management and the systematic and system level assessments. Today I'll be talking only about the systematic approach. The systematic analysis aims to deliver an unbiased overview of the literature-based evidence. It involves applying a very strictly controlled methodology termed the systematic protocol, and the work is a major undertaking, involving gathering, sifting, and data extraction of many papers. Also, throughout this process, regular consistency checks are necessary among those screening the papers and gathering the data to make sure that everybody is on the same page and pursuing the protocol consistently well. Here, a systematic map protocol was applied, as opposed to a systematic review. The systematic map catalogues the approaches that address a specific research question, and here that question is, what evidence exists on the effectiveness of techniques and management approaches used to improve the productivity of field-grown tomatoes under conditions of water, nitrogen, or phosphorus deficit? Here we show the three main phases of the systematic process: searching, screening, and synthesis. You can see that the strict search terms of different databases identified 19,829 records in total. Also, that from the summary of processing the records, we were left with only 223. This is just 1.1% of the original records identified, and with most exclusions occurring on the basis of records being either duplicates or because of their title. So here's a snapshot of the findings. Of the 19,829 papers identified, only 223 actually addressed the research question. And we found that 51% of the papers were reported from just 3 countries. Looking at basic details of experiments from records selected for data extraction, we see that study length was short and there were no long-term or crop rotation studies. Also, that transplanted types accounted for at least 86% of the studies. While 1/4 of the studies did not specify the soil type, most test soils appeared to be free draining. In conclusion, soil data was often not recorded, as for pH, poorly recorded, or recorded with great inconsistency, including differences in units and choice of soil classification system. 126, around one half of the papers used for data extraction, assessed resource use efficiency, that is, resource use with respect to fruit yield. Furthermore, only a small number of trials assessed combined stress tolerance, with only 10 papers assessing water, nitrogen, and phosphorus simultaneously. In terms of the methods tested, few trials explored integrated methods, with only 8% of studies using 3 interventions or more. We could distinguish 8 different methods or intervention groups that impacted on the yield of field-grown tomatoes. The largest intervention group studied was irrigation, reported in over 39% of all studies, followed by fertiliser-based approaches at 21% of the records, and then crop and soil management at 15% of the records. The remaining 5 intervention groups accounted for less than 10% of the evidence assessed, and these included, in decreasing use, soil amendments, biostimulants and biofertilisers, breeding and genetics, technochemical approaches, and finally, computer-based approaches. This bar chart shows the 11 different forms of irrigation interventions reported in relation to their impact on the yield of field-grown tomatoes. You can see that drip irrigation was the most reported and the most effective, followed by deficit irrigation, where crops were conditioned to cope with stress. Other forms of irrigation are not commonly tested with respect to crop yield. Here you can see the 5 different forms of fertilisation intervention that were reported, and it appears that applications targeted to either root or shoot are more likely to be effective to ensure yield under resource-limited conditions. Looking here at 6 different crop and soil amendment interventions, cover crops were not always effective, despite being most reported. In contrast, manipulating plant density was almost always effective, followed by mulching, though there were a range of other more novel methods which were effective too, such as the use of geotextiles. Of the 21 studies assessing tomato yield in response to applications of biostimulants or biofertilisers, PGPRs or plant growth promoting rhizobacteria were almost always beneficial, or that negative results are simply not being reported for the PGPRs. In contrast, AMF was effective in just over half of the trials. Looking at reports where technochemical, breeding and genetic, plus computer-based interventions were used, breeding was the most common by far. Other interventions, which surprisingly include precision agriculture, were not commonly reported. Considering the most common and effective interventions we found, some appear much more prevalent than others. Drip irrigation was successful in 21 of 49 papers. Compost, the most common soil amendment, was effective in 11 of 12 papers. As we said before, plant growth promoting rhizobacteria also was effective in all the reports. Breeding in around half of the papers, and genetic modification only appeared in 2 papers but was effective in both. The implication of the findings is that we know less than we thought, or that we'd achieved less than we expected. Crucially, reporting of breeding for multiple stress tolerance is limited, and we really need data from more long-term innovative rotations particularly those that are mixed rotations where vegetable crops and fruit crops are combined with arable crops. The evidence base from these platforms can be really powerful, especially where they integrate multiple interventions at the same time. This evidence base is really important if we're to address the climate change, nutrition, health nexus that faces us. Overall, we need more concerted action if we are to climate change proof our crops. If this is what we're finding for tomato, I would expect the situation is much worse for most, if not all, the other crops. For any one systematic approach exercise, there are usually two publications. One, before the protocol is applied, that is, the protocol must first be peer-reviewed, agreed, and published before it is used. The protocol applied for the TOMRES systematic map already features in the journal Environmental Evidence. The systematic map findings were submitted to the same journal as the second manuscript for publication. Though note, the results reported in the second paper will not describe the relative success of each intervention. Only the list of interventions and their relative occurrence will be reported in manuscript 2. The extent to which each intervention was positive, neutral, or negative relative to yield will be reported in a third TOMRES deliverable known as the system level assessment. The system level assessment will also form a synthesis of project activities as a whole. Application of the systematic approach takes considerable time and labour, and normally 18 to 36 months are required to apply conventional methods. I therefore highlight this Nature paper to you, which was published on October the 12th, 2020, and which shows the utility of automated machine learning to speed up the systematic approach. Despite our best efforts, bias still exists in our scientific endeavours, and these need to be carefully guarded against. And we still see bias even in our systematic approaches. For example, in this study we see there's been what's called Tower of Babel bias, where we retrieve English-only records. There's a need to translate articles, perhaps automatically, and that will improve the insight. There's online-only bias. Many studies are not available online, and in this case, 58% of our total were not available online. That is a very significant knowledge loss. There is also coding bias, and that is data was captured according to subjectively chosen characteristics. This characterization bias or coding or filtering of the interventions means that interventions pulled into groups can lead to the hiding of important nuances for some interventions. So we do need to be careful as we interpret these results and be mindful that we've probably lost some important insight. Finally, I'd like to thank my TOMRES partners and publication co-authors. Special thanks are conveyed to Fanny Tran and Nora Quesada for bearing the brunt of the work here. I also thank you for listening, and please do get in touch if you have any queries or would like to discuss the approach or findings presented.
Thank you very, Pete. Maybe Pete would like to follow up with a few words on this presentation that he pre-recorded. A very impressive effort, Pete and team, that you carried out to screen all this literature, although you only screened 42% of the available. Quite a huge effort.
Yeah, it was certainly very difficult. A lot of time was spent getting the consistency check right. So that is just taking a subsample of the papers and making sure that all the co-authors, all the other people judging the papers were judging papers in the same way, because we found there was quite low consistency to start with. And every time you do that, you had to work out why there was low consistency. And of course, it was to do with something in the guidelines to each of the assessors. So an awful lot of time was spent just making sure that we were hitting a very, very high, above 90% consistency rate with the papers that we were processing. So it's certainly an interesting exercise for me. I've never done a systematic protocol before, obviously with one paper already published. The second paper that we submitted to the journal was actually rejected. So, and it was rejected because they wanted the methods mapped, but they didn't want to trap information where methods were effective or not. I thought that was quite interesting. So they regarded that as bias. So while I could say how many methods were being used, I was not allowed to report, we were not allowed to report which ones reported a positive, neutral, or negative effect on yield. So on one hand, I could respect the judgment, that is the framework for a systematic review, but as a practitioner, I think that's lost information. Could be regarded as lost information. So what we intend doing now is we'll have that one publication on the method, the protocol. We'll publish the systematic review where we just map the interventions without saying anything about how good or bad they were for yield. And we'll build the information that we weren't allowed to include into a third paper, which will be the system level analysis for TOMRES. And we'll combine that information with perspectives from the other work package leaders as well. But I think it's worth mentioning as well, there are other forms of bias that I didn't mention. One of those forms of bias is editor's bias. It's quite recorded, and particular editors have a liking for particular techniques and particular methods, and they favor those in their journal, often discriminating against others in the same process. So I haven't looked at editor's bias, but if we chose to, we could dig into the journals to see if editor's bias was also apparent. That might be controversial to do. Also, if you look at some of the interventions, particularly PGPRs, and I see this in the literature as well, people are quite happy to report negative or certainly neutral and negative effects for arbuscular mycorrhizal fungi. But they're less likely to do that for PGPRs. Negative PGPR results are often not published. I don't know what to make of that, whether that's a difference between the ease with which PGPRs can be studied relative to AMF, or whether people just have a thing about AMF. They don't like them so much, they're happier to publish negative results. But certainly digging into it is quite interesting. But if anybody has any questions, I'm quite happy to answer them now quickly, or you can email me at some future date. Thanks.
Okay, thanks, Pete. I suggest that you keep all your questions to Pete until the general discussion that we have at the end of the workshop, because maybe also then by hearing and listening to the other two presenters, then we can find some common ground and some synthesizing discussion. Thanks very much, Pete, again.